Okay, so we should start. Welcome back. So now we have a seminar, and our speaker is Nele Callebaut from the University of Cologne. And she will talk about radial canonical ADS3 gravity and TTbar theory. So this is a talk which is very much connected with my lecture on the problem of time in quantum gravity and in the context of the Wheeler-DeWitt equation. And that will also be connected with the last lecture I will give in 2 weeks on Wheeler-DeWitt and ADS. So with this, Nele, please, yeah, you can start.
Thank you very much. So, with the mic on, sorry I had to run because I forgot my jacket. Thank you very much for the invitation. It's great to be here. And indeed, I want to talk to you about radial canonical ADS3 gravity and TTbar, as the title says. So this is based on the paper with that archive number with my student Blanca, who's at Cologne with me, and then two collaborators from the UK, Matt and Cyril. Right, so as an introduction, we all know and love ADS-CFT or holography as the modern, I should say the most popular modern approach to quantum gravity. And so in a sense, we believe that we know the answers to the quantum gravity problems, but we know them in an encoded way, in an intricate encoded way in field theory data. And the whole program of ADS-CFT is to try to extract trying to build a holographic dictionary that extracts the answers to quantum gravity out of that CFT data. Good, and then on the other hand, we have the more traditional canonical approach or Wheeler-DeWitt approach to quantum gravity. And in this original approach, you very quickly run into problems, most of them related to the treatment of time. Good. So in some sense, Wheeler-DeWitt tells us what the questions are in quantum gravity, and somehow ADS-CFT knows what the answers are. So it's natural to want to connect these two approaches again in the hope that we can connect answers to questions. So for that reason, we're interested in studying the canonical or Wheeler-DeWitt approach applied specifically to three-dimensional, in this talk, negative cosmological constant gravity, which I'll refer to as ADS3 gravity. Okay, so this is with the optimistic reasoning in mind that we could connect questions to answers at some point, but at the very least, if you don't follow that argument, we want to combine insights from Wheeler-DeWitt and holographic approaches. And so here I list a list of references that follow this approach using Wheeler-DeWitt techniques in ADS-CFT research. So here's a list of references. Most of those are in low-dimensional holography, so 2D or 3D bulk. And then here's a list of slightly more recent papers, and in particular, the first one called Cauchy slice holography does make claims about building a Wheeler-DeWitt formulation of ADS-CFT. And this paper heavily makes use of a theory called TTbar. So let me next discuss TTbar. So TTbar indeed is a key concept in translating between ADS-CFT language and Wheeler-DeWitt language, or a bridge if you want. And that is so because the TTbar path integral has been holographically identified with the gravitational wave function psi that solves the radial Wheeler-DeWitt equation in ADS3 gravity in this paper by Magot, Mazay-Verlinde. So what is this TTbar theory? So here's the definition, and the definition is given in terms of a flow equation for the action as TTbar as you vary the TTbar coupling lambda, or deformation parameter lambda. So as you dial that parameter, you're continuously deforming with this TTbar operator, which is equal to this particular combination of stress tensor components. Right, and so if the initial deformation is applied to a seed theory that is a conformal field theory, then this just becomes T bar, no trace if you start with a CFT, hence the name TTbar theory or TTbar deformation. Okay, I just want to stress that the importance of TTbar here. So the TTbar deformation tells us in field theory language how to move into the area's bulk. So I do believe TTbar theory is very important to really understand the holographic dictionary, because it, in a sense, dissects area CFT for you. Okay. So the plan now is to study radial canonical areas 3 gravity, as I mentioned, the radial Wheeler-DeWitt equation just now. And we'll study this in two ways. The first is using an ADM deparametrization strategy. And the second is to consider the radial Wheeler-DeWitt equation. First, construct a classical areas geometry solution from that, namely rotating BTZ, and then use that classical solution to construct a semi-classical wave packet solution to the radial Wheeler-DeWitt. So, and in both these cases, we'll discuss the TTbar interpretation or holographic interpretation, which I'm now using interchangeably. Okay, so to start with the first part, the ADM deparametrization, I want to start with discussing the concept of deparametrization in a very simple context. So I will discuss parametrization and deparametrization in a simple mechanics model. So I want to look at a simple action of the form PQ dot minus H in terms of canonical pairs of coordinates and momenta for a system that has m degrees of freedom. So the index I runs over these m values. And now I can take the time and the Hamiltonian, group them together, and interpret them as an extra canonical pair. I call them Qm plus 1 and Pm plus 1, depending on an arbitrary parameter tau. And if I do that, then the second term in the action just takes the same form as the first term. So the whole action looks like this, where now J runs over one extra canonical pair. So there's now m plus 1 canonical pairs, and I'm using the index J as opposed to I for J running over a larger range of values. Okay, so in this notation, there's more degrees of freedom because I'm running over more indices. Good. The thing to remember in this notation is the identification of this extra momentum as the Hamiltonian. Okay, there's two ways to remember that. So in this line, I just explicitly wrote it here as a condition. And another way to remember it is by using a Lagrange multiplier n that enforces a constraint h, curly h, that enforces a constraint curly h, which as a solution has the condition that we want to impose, namely Pm plus 1 equals minus h. Okay, so then we've arrived at the end at this form of the action. It's called a parametrized form because it's given in terms of this arbitrary parameter tau. And it has more degrees of freedom. So our parametrized form has more degrees of freedom, but this is balanced by the fact there's now a reparametrization invariance in the system. Okay, I'm copying here the deparametrized form that we started from. So that I don't have to scroll up. And we can compare the original form with the final parametrized form. So what we did now is the process of parametrization, going from this original PQ dot minus H form to parametrized form. So if we retrace those steps, then we can follow how to do a deparametrization. Okay, and that deparametrization is a two-step process. It consists of substituting the constraint solution. So starting from here, you solve the constraint, curly h is 0. You solve it, plug it back in here, so this term is gone, and we're only left with this. And the second step in the deparametrization process is then to impose what is called a coordinate condition. So in this line, the point is that qm plus 1 of tau, this function is undetermined. It's equally undetermined as the Lagrange multiplier. And so we can choose it. And you can make a particular choice, and that's called a coordinate condition, and call that choice time. So this first step identifies pm plus 1, the second step identifies qm plus 1, and it tells us, gives us a procedure for deparametrizing a deparametrized action. I forgot to mention here that you can think of this curly h as an unphysical Hamiltonian, starting from the system with the physical Hamiltonian h. Good. Right, we have this two-step deparametrization process, and what it does for you is it identifies a preferred time that we call t. It identifies a corresponding physical or true Hamiltonian, and it identifies corresponding true or physical degrees of freedom, which were the original degrees of freedom. So this is the concept of deparametrization, and it's the basic idea behind the ADM approach to gravity. So with that, we can now switch to gravity. And I want to summarize the canonical approach to quantum gravity. So the starting point would be the Hamiltonian formulation of GR. So originally, we're in 3 + 1 dimensions flat gravity. That's the setup. And we can write our metric in an ADM parametrization, which is given here. So in terms of a lapse n, a shift ni, and these gammas, which are the intrinsic metric on the hypersurfaces or slices sigma that foliate your space-time. And it's these gammas and their canonical partner pi that take the role of q's and p's, or coordinates and momenta, in the sense that if you insert this ADM ansatz into your gravitational action will take this form, which we recognize as a parametrized action, where the lapse and the shift act as Lagrange multipliers, imposing constraints. So in particular, the lapse imposes what is called the Hamiltonian constraint, curly h is 0, which is a quadratic Hamiltonian h in the momenta. Good, and so far what I said was classical. Now if you want to quantize, the canonical procedure would be that you promote your momenta to variational derivatives with respect to the q's. So with respect to the 3 metric on the slices, as these pi's act on gravitational wave functions in the coordinate representation, quote unquote. So if you do that in the Hamiltonian constraint, then you end up with a condition on allowed gravitational wave functions in the form of a differential equation that is called the Wheeler-DeWitt equation. With here I'm writing out the gravitational wave function. So what I mean by the gravitational wave function in the coordinate representation is that this psi depends on gamma, or your q's, and it depends on gamma by this condition that the bulk metric on the slice equals gamma. Okay. And now we turn to ADS3 gravity instead. So ADS3 gravity means that now we're in 2+1 dimensions with a negative cosmological constant. And instead of considering slices that foliate space-time in a time-like manner, we want to do a radial slicing. And for that, we need a radial ADM parametrization, meaning that the lapse is sitting in front of a space-like coordinate in the metric. But for the rest, this is the same type of ansatz. Now that we're in ADS3 gravity, our gravitational action does not only have Einstein, Hilbert, and Gibbs, Hawke, and York term, but it also contains what is called a counter term. So this is necessary for making sense of the asymptotics of your theory. So this will be included. Okay, and again, same thing. If you substitute that ADM ansatz into the full gravitational action, including the counter term, then it takes this parametrized form again, where now I do write out what the momenta are, what this Hamiltonian is that is set to 0, and what this HI is. Okay. Okay, so basically the Hamiltonian is indeed quadratic in the momenta, but there's also a term linear in the momenta. And that one is there precisely because of the counter term. That's why this one appears. And then what you can do is go to a symmetric ansatz for your metric, typically called a mini superspace ansatz, where all the functions that appear in your metric only depend on R rather than on all the coordinates. And if you do that, then your sigma slices will not intersect, and your momentum constraint will be automatically satisfied. So if that one is automatically satisfied, what we're left with in this parametrized action is just this part. So I'm going to copy this on the next slide, and also the H. Right. So this is our system. And the point is that you can perform a deparametrization procedure here and bring your gravitational action in this original PQ dot minus H form. Okay, and to obtain such a PQ dot minus H form, the deparametrization procedure is that you solve this Hamiltonian constraint and plug that back in. So here basically what you do is you solve roughly for pi, for the trace of the momentum. Really you solve for a rescaled pi. But because this is a quadratic equation, it means that the solution will take a square root form. And this is the square root that you see appearing here. So you're solving the constraint for a solution that takes this form that identifies the Hamiltonian as an extra momentum. So there's an extra momentum, Pm plus 1 equals minus some h. Okay.
Is it clear that the argument of the square root is always positive? I mean, the curvature could be very negative or not? So the last term, I mean, the first two terms are positive, but the last term is z squared r over 2.
Yeah, the r of your slices.
Negative or not too much? Or maybe it doesn't matter?
Well, I'm wondering if so at some point I'll discuss the TTbar energy levels that also have a square root, which can become imaginary because the square root can become negative. I'm wondering if it's related to what is precisely here. I didn't Yeah, I'm not sure. But the point being that if it does become imaginary, there's a dual interpretation to it. Because then it has to be that, or related, yeah. Good, so you solve for this rescaled trace of the momentum to get some square root solution. And one thing to notice here is that the form of the Hamiltonian constraint is already suggestive of solving it to something of this form that isolates the momentum, precisely because there's already a term that's linear in this pi. So it already suggests to solve for this pi and write it as momentum equals something that you can then identify as a physical Hamiltonian. Like I stressed, this term comes from the counter term, so the asymptotic physics is important here. Good, so that was a remark. Then the new coordinates that appear are this, what I called V and its canonical partner, and what we called gamma tilde and their canonical partner. And so here I'm writing in pink what roles these objects play in the simpler mechanics, mechanical model discussion. Okay, but I haven't told you how they are defined, so let me do that. So this V is the volume of the slices, well, basically the volume density, but I'll keep calling it volume. So the square root of minus gamma. Its partner is this rescaled pi that I was talking about. So rescaled with the volume, and it's referred to as York time in flat gravity literature. And then we have the gamma tilde and pi tilde, which we recognize then as true degrees of freedom in this procedure. And these are objects that have the properties that this tilde metric has a determinant equal to 1, and this tilde momentum has trace 0. So those are the properties of these objects. But the main point is that we've recognized this volume V as the preferred time. But okay, I'm using time, but we're doing a radial slicing. So V is the preferred radial time. And so let me give some comments on why this is maybe to be expected, or at least consistent with other statements. So using the volume as time is something that is done typically in the Sitter cosmology, where the direction of expansion is your volume. And that means that it's natural that the volume takes the role of a radial time in anti-de Sitter. Okay, so that's one thing. Then these variables that we introduced, they are called Dirac variables in the famous Regge-Teidelborn paper. So they're used there as well, and in general it's known that the volume gives you time direction on superspace, superspace being the name for your configuration space, so the space of gammas. Okay, so those are all consistent with the deparametrization story that we see here. Okay, this is just to repeat the deparametrized form, of the action that we find, which involves identifying a preferred radial time, or volume time in this case, with an associated physical radial Hamiltonian density, which is this York time, and associated physical degrees of freedom, which are the gamma tilde and pi tilde. So physical or true or ADM all refer to the same thing. Then let me also repeat the statement of rewriting the action in terms of the on-shell variation, where the corresponding statement would just be that if you write out this on-shell variation in terms of the new degrees of freedom and the new coordinates, that you don't get any mixing terms. And the reason that you get this nice split and no mixing terms is precisely because of the properties of these Dirac variables, the trace being 0 and the determinant being 1 of this guy and this guy. All right, so then upon quantization, you would promote this momentum to variational derivative, and this line would become a Schrodinger equation version of the Wheeler-DeWitt equation. So this is a volume times Schrodinger equation with, again, the ADM Hamiltonian taking the square root form structure. Okay, so now let me move to the holographic interpretation of these results of our ADM deparametrization discussion. First of all, the true degrees of freedom gamma tilde that appear, or the ADM degrees of freedom, they are interpreted as the conformal boundary metric of the ADS3 solution. And the Wheeler-DeWitt equation, or at least the asymptotic Wheeler-DeWitt equation, contains Weil anomaly physics of your dual CFT. Okay, meaning, so by Weil anomaly physics, I mean behavior of that dual CFT under variation of its scale, of that theory under variation of scale or volume. So the way to see that the asymptotic Wheeler-DeWitt equation contains Weil anomaly physics, you can see that in two ways, using the Hamiltonian constraint. Then the dual physics can be read off in terms of the dual CFT stress tensor, or you can read it off from let me scroll down from at the level of the Wheeler-DeWitt equation, then in terms of the CFT partition function. Okay, so let's go a bit slower, go back up. So, point is, asymptotically, your ADM Hamiltonian density becomes just proportional to the curvature of your slices. And this is sitting on the right-hand side of your Hamiltonian constraint. So your Hamiltonian constraint asymptotically just takes this form. So asymptotically meaning in the near boundary or large volume limit. And this directly expresses the Weil anomaly of the holographic or large C CFT because your York time is directly dual to the trace of the CFT stress tensor. And the Weil anomaly is just this statement about the trace of the stress tensor. Okay, so what I'm using here is the Brown-Henneaux central charge that gives you the standard relation between dual theory parameters. Yeah. And the other thing I used was just the definition of the Brown-York stress tensor. Okay, then at the level of the Wheeler-DeWitt equation, in this Schrodinger form again, the right-hand side is again just proportional to R acting on psi. And this directly expresses this statement about the CFT partition function, which is the conformal Ward identity of the CFT. Okay, so the variation in V in the dual CFT is a variation of the scale of that theory. So just to make clear, the gravitational wave function depends on gamma through its boundary condition, as we discussed. And that boundary condition sets the source dependence of the CFT, holographic CFT, with the holographic CFT partition function depending on gamma as a background geometry or source. Yeah. Okay. Right, I'm repeating here the comment that the counter term is the one responsible for the linear term in the Wheeler-DeWitt equation. Again, because it's that counter term or that asymptotic physics that is important in the discussion of the Weyl anomaly physics of the CFT. So really what we're doing here is repeating standard holographic statements in ADS3 gravity, but we're repeating them using this volume time notation, and the claim is that that volume time gives you a particularly concise way of making those holographic statements, because pi v, for example, is exactly the trace of the CFT stress tensor. And so the ADM deparametrization results are particularly revealing of this dual CFT structure. Right, so to summarize the volume, we've given in the previous slide, a volume time reformulation of Friedal's formulation of ADS CFT, which is the beautiful formulation that the asymptotic Wheeler-DeWitt equation, radial Wheeler-DeWitt equation, is solved by the CFT partition function. And the second point is the holographic renormalization, particularly in the Heemskerk-Polchinski version, who also write down a Schrodinger type equation in that paper. Good. So let me continue with the holographic interpretation. So far, what we've discussed is the interpretation asymptotically of the Wheeler-DeWitt equation. So we can remove this limit now and look at the full radial Wheeler-DeWitt equation. So this brings me back to the statement of the introductory slide, which is that the full Wheeler-DeWitt equation contains information about dual TTbar physics. Okay, so meaning that if you vary the volume further, it corresponds to TTbar deforming your dual theory with TTbar coupling that is inversely proportional to V, to your volume time. Okay. Sorry. So to see that, let's look at the Wheeler-DeWitt equation in the Schrodinger form. So using the volume time expression. So this then expresses dual physics in terms of the partition function. So, and what it expresses is a flow equation for the TTbar partition function. So this line you could write down from the flow equation for the TTbar action, which is the definition for TTbar that I gave in one of the first slides. And that you can match to this form of the Wheeler-DeWitt equation with the following relation between bulk and boundary objects, that the gravitational wave function is your TTbar partition function. The ADM Hamiltonian density gives you the expectation value of the TTbar operator, which works at large C. And your TTbar coupling is given in terms of bulk parameters like this. So what we're doing here is, by using the volume time description, is treating TTbar really as the extension of the holographic Weyl anomaly further into the bulk. Okay, so this was at the level of the Wheeler-DeWitt equation. We can also make a statement at the level of the Hamiltonian constraint, and that we expect to tell us something about the dual theory in terms of the stress tensors of the dual theory. And indeed, if you add the non-asymptotic terms back in to the full Hamiltonian constraint, then the full thing expresses what is known as the trace flow equation in TTbar. So this is the dual interpretation. This was discussed in McGowan, Mazet, Verlinde, where the object between the brackets is the expectation value of your TTbar operator. And it's a whole thing that the expectation value of this operator, that it factorizes the way it's written here. And in particular, that factorization property holds actually for all values of the central charge in the case of the flat space TTbar operator. So what this means is that there is actually a beyond large C interpretation of this dual interpretation, which would be that TTbar chooses or defines a particular normal ordering, and thus a particular quantum gravity theory and Wheeler-DeWitt equation in the bulk. So the normal ordering that TTbar would suggest would be the one where you normal order this version of the Hamiltonian constraint rather than the Schrodinger equation version where you would normal order a square root. So that would be a different theory actually, but the same asymptotically. So what it does do for you, though, the volume time identification, is that it recognizes the structure of the Wheeler-DeWitt equation as being something linear equals the rest. And that is what you need here upstairs. Something linear equals the rest for this TTbar interpretation. Okay, and a last comment that I wanted to make about this is that the most precise statement of the most precise version of the statement that I also mentioned in the beginning, that the TTbar partition function equals gravitational wave function, can be made in the Vielbein formalism. So discussing the radial Wheeler-DeWitt equation in Vielbein rather than metric formalism, and then you can write down a solution in the form of an integral transform of the CFT. That's also in Radial. And that would be the most precise version of this statement. Okay, so that was it for the holographic interpretation. Then I wanted to say something. So using this volume time, we can also discuss the Laplace transform between the Dirichlet and the conformal boundary condition problem. So let me just spend one slide on that. So here we're looking at our gravitational wave function. It depends on the boundary data through these boundary conditions that were imposed, which are Dirichlet boundary conditions. And I'm writing here the variation, the on-shell variation for the system, which takes such a form that it tells you that you will have a good variational problem if you fix gamma tilde and v. Okay. So this would be the Dirichlet problem here upstairs. And then you can take that gravitational wave function and Laplace transform it like this. To obtain a new gravitational wave function where the v dependence is basically replaced by York time dependence. And this new gravitational wave function is written in terms of a new action given by this, with a new on-shell variation that tells you that you should fix as boundary conditions gamma tilde, but not the volume. Instead, you should fix pi v. And fixing these things is what is known as conformal boundary conditions. So you went to conformal boundary condition problem. Conformal boundary conditions typically are set to fix the gamma tilde and the trace of the extrinsic curvature. But that comes down to the same thing, so let me... your York time is basically roughly, it's equal to k. So it's the same thing. I'm adding here for completeness what type of actions these are in terms of the k dependence in the Gibbons-Hawking York term. But the point would be here that the Wheeler-DeWitt equation that you'll obtain for this new gravitational wave function will take such a form that describes Schrodinger type evolution, not in volume time, but in York time. Your York time is well, pi v, or its trace of the extrinsic curvature. And these conformal boundary conditions have been discussed by Witten in the context of ellipticity of the Wheeler-DeWitt equation, stating that these would be the more well-defined boundary conditions and therefore give you well-defined wave function in perturbation theory. So that's why I'm adding this.
Still radial quantization in your case? Or?
Yes, yes.
While Witten was more like standard time.
Yes, but there's part of Witten that also applies to the radial discussion, because he also discusses the TTbar interpretation at some point. So okay. I think it applies to both. But
because I guess the signature of the metric is different. Of the r equal to constant slice, it's Minkowskian signature.
Yeah, yeah.
But I don't know if that changes or not.
Yeah, me neither. I haven't thought about this further. But it's just to mention why people are interested might be interested in this York time version. Right. Because there are some people researching this conformal boundary conditions in the context of ADS-CFT. I'm not quite sure if it's radial or time-like, but yeah. Okay, and then this brings me now to the second part. That I wanted to discuss. So the first was ADM deparametrization strategy, and now I want to discuss how we can obtain the BTZ solution and a corresponding wave packet solution to the radial, starting from the radial Wheeler-DeWitt equation. Good, so starting point is again the same radial ADM ansatz for the metric that we had before, except that I've added here this epsilon, which is just a sign. It's because we want to construct the BTZ geometry in one go, both in regions where R is space-like and in regions where R is time-like. So that's why we use this notation here. And then we take the Hamiltonian constraint. And so this is quadratic in the pi's, and we replace all the pi's with their expression in terms of the on-shell action. And that gives you what is known as the Hamilton-Jacobi, the gravitational Hamilton-Jacobi equation, which is the classical limit of the radial Wheeler-DeWitt that we've been discussing. So I've written it out here. And you can solve this, find a family of solutions of on-shell actions in terms of Hamilton-Jacobi constants of integration.
So the counter term is not appearing here?
No, thank you. I forgot to mention. So yeah, because there's only quadratic ones. So this part of the paper is without the counter term, and we add it back at the end.
Okay.
which is another way of proceeding. This is basically because this is following the same strategy that appeared in this paper mentioned on one of the first slides by Hartnell. So Sean Hartnell had this paper also 2022 discussing how to get an ADS4 black hole solution in this way. And so we're following the same strategy, which means that indeed we decided to not include the counter term at this point, but later. Okay, so you find this family of solutions, and then the procedure in Hamilton-Jacobi theory to solve further for a solution to the Euler-Lagrange equations of your gravitational Lagrangian involves like imposing these additional conditions on the dependence of the classical action on extra constants here. And this you can solve further, then you find gammas in terms of one of the gammas, so it's a relational solution, and in terms of all these integration constants that appear. And so we take the gamma phi phi in metric function and call it r squared to have the normal BTZ radius notation sitting in front of the d phi squared. And if you do that, then knowing this solution, then you can plug everything back in the ADM ansatz upstairs and find this standard form of the BTZ solution indeed. Where this f is our redshift factor given here in terms of our hj constants, and so it's clear that the Hamilton-Jacobi constants are indeed the mass and the rotation of your black hole. Okay, so this is a classical solution. Now there's a very simple way to go beyond the classical beyond the classical discussion, which is to take our classical solution and exponentiate it, and this will give you a semi-classical Wheeler-DeWitt solution to the Wheeler-DeWitt equation. And in particular, the choice that we've made here is called the Vilenkin wave function solution to the Wheeler-DeWitt equation. And that's because we've chosen a definite sign here in the exponent. So there's other solutions that you can make, which would be combinations of this one with the plus sign in the exponent and the same thing with the minus sign in the exponent. But if you don't do that, you call it a Vilenkin solution. So there's a choice of sign here by considering the Vilenkin solution, and that choice of time you can see here in the representation of our BTZ geometry. The choice of time corresponds to a choice of evolution as you cross the horizon, because the sign of what is sitting in the exponent will come down if you act with a momentum operator. So that sign tells you about the direction of evolution of your slices. And so choosing the plus sign means that as we reach the horizon, we decide to evolve the slices upwards instead of the other possible option, which would be to evolve them downwards. So with this choice of sign in the exponent of our solution, we've chosen a direction of evolution beyond the horizon. And because there's two options, it means that we've broken time reversal symmetry at this stage. And so you've broken time, or you've broken, CPT symmetry. And there's a dual interpretation to that, which is that it's consistent with this non-unitarity that appears in TTbar, meaning that TTbar is a theory that has energy levels that can become complex. And indeed, they become complex precisely when your TTbar crosses the horizon. So you can see that from the expression for the energy levels. So these are the energy levels of TTbar. You can calculate them in TTbar or using the holographic dual. And it will take this square root form where what's sitting under the square root is precisely the redshift factor of your dual BTZ geometry. And so it means that in the red regions in this diagram, where the redshift factor is negative, the TTbar energy levels will become complex. Good. So indeed, the blue regions have a space like R and therefore a positive redshift factor. And the red regions have a time like R. And so what I've done here, we've constructed the rotating BTZ geometry, but I've just drawn the diagram for the non-rotating one for definiteness, but I can add here the rotating one and also the version of the previous diagram with the first part of the evolution, the blue part of the evolution in Euclidean signature. So this would be like preparing the state like this and then evolving forwards in a chosen direction of time. And one final diagram here is plotting the volume time for the BTZ solution. So this epsilon appearing here is precisely the sign that appeared in the ansatz. And so our volume time starts at minus infinity asymptotically, then becomes 0 here at the horizon, and keeps being a monotonic, so well-defined radial time up to the maximum volume slice. But the maximum volume slice is behind the horizon. A lot of things already break down near the horizon. So that's good enough for us for the volume time discussion. Right. Good. Then, yeah, here in this slide, I mainly wanted to discuss the DeWitt metric because we'll need it in the next slide. But I'll also write a normal ordering choice, which is different from the volume time Schrodinger form. Good, so our curly H Hamiltonian, the one in the Hamiltonian constraint, like we said, it's quadratic in the momenta, so it takes this general form. Again, this is indeed in the discussion excluding the counter term. So it takes this general form, which means that you can read off from the form that you have what this big G AB is, and that is the DeWitt metric, which is the metric on configuration space, which we call superspace or mini superspace. And once you have that DeWitt metric, one standard choice of normal ordering in going to the quantized version is what is called Laplace normal ordering, where you use the Laplacian for the DeWitt metric, and this second term is in terms of the curvature of the DeWitt metric, and that here's V again. So the second term is present if you impose conformal covariance of this equation, not just covariance. So I'm adding this for completeness. This is a term that depends on the dimension of your mini superspace. But also for the next slide, when we discuss the wave packet solution, it's fine just to stay at a leading order in the semi-classical approximation, and at that order, the choice of normal ordering and also this extra term for conformal covariance that appears are not really. They don't matter at that stage. Good, but really what we need is the bit metric. We'll need it for our norm. And so I've written it here for... written it here so we can use it next. Okay. Right, so next is to construct a wave packet solution to our radial Wheeler-DeWitt equation using our classical solution. And so you can do that by taking our Vilenkin wave functions and then constructing a wave packet like you would by using a Gaussian wave packet beta, which is centered on classical values of your Hamilton-Jacobi constants. With widths delta C, delta J. Right, and then here we discuss the DeWitt norm, which we'll use for our wave packet solution to calculate expectation values. So for a given choice of clock in your mini superspace, the DeWitt norm is given by this formula. So it's dependent on which choice of clock that you made. So it's sitting here in the notation. And what's appearing here is again sort of a Laplacian choice. So you need this the DeWitt metric for writing this norm. So this is Hermitian conjugate. So you can write a DeWitt norm given a choice of clock in your mini superspace, and then when you've written that norm, you can calculate expectation values of other Q's in that. And so that is what we do for a particular choice of clock, namely gamma phi phi, which we called the BTZ radial direction squared. The DeWitt norm takes this form. And then you can use that norm to calculate expectation values of other configuration space variables, for example, gamma TT, in your wave packet solution. And I'm giving you here the answer, for example, for this one, but these become very involved calculations very quickly. But the physics of it remains that what you find is basically the classical value plus corrections in the bits of your Gaussian constructions and corrections in H bar. So, and in particular, you can calculate this variance here. And what you find is that this becomes large quickly under radial evolution, and especially when you reach the horizon, which can be interpreted as that quantum effects dominate and your wave packet description breaks down. So this brings me to a summary. So we studied radial canonical ADS3 gravity in two ways. The first was ADM deparametrization. And what we find there is that we identify these gamma tildes as true degrees of freedom or physical degrees of freedom. And this reveals degrees of freedom for the description of your dual physics. So we discussed the holographic interpretation here. And secondly, we discussed that there's an interpretation of the radial Wheeler-DeWitt equation as a volume times Schrodinger equation, So the dual statement would be that the TTbar partition function for large C satisfies that volume times Schrodinger equation. So these would be the results of that section. And then in the second part, we constructed a rotating BTZ, classical geometry solution, and the corresponding semi-classical wave packet solution to the radial Wheeler-DeWitt equation. So first statement is that the construction of the solution from the Hamilton-Jacobi equation is possible. It's not clear that, for example, in higher dimensions for Kerr, for example, that it is. And the main result of the wave packet discussion is that the wave packet solution predicts a breakdown of the semi-classical description, especially near the horizon. And then I've added two short outlooks. One is whether we can use this York time interpretation of the Wheeler-DeWitt equation for the conformal boundary condition problem wave function to study conformal boundary conditions, and also what role they would play in the whole TTbar discussion. That would be one thing. And I'm also interested in beyond semi-classical TTbar interpretations of the radial Wheeler-DeWitt, but particularly in the metric formalism. So as I mentioned, the Vielbein formalism is more clear, but the metric formulation is much less clear. So that's all I wanted to say. Thank you.